Okay, let's get started, right? So thank you for being here, and thank you for choosing this talk. I wish I could attend the workshop of Lian, as was mentioned in the keynote, but hey, we are here, and I'll do the best I can to give you some different perspectives, some different talks. So there's not going to be any demo. Koray did a great job to recover, but because this talk is about chemistry, so if I had to do a demo, I might have killed you all because I haven't done chemistry for a while, but I'll explain in a bit. So this talk is called the Periodic Table Cloud Native, and I was inspired by other talks, of course. There was a George Castro, which is a CNCF DevRel, had this talk about dinosaurs and history and cloud native. So I thought, I can do something like that. And what do? What is my background? Is chemistry. So I had this idea of comparing or explaining cloud native through the periodic table. So it's a journey through chemistry, cloud, and love. These are some of my passions, some of the things that trigger me and then that keeps me going. So I have 1,500 seconds, so I better move fast. And now for something different, right? So Monty Python, now for something completely different. Something that you don't need to pay much attention. You can actually fall asleep like I did. I'm guilty of falling asleep doing chemistry at the university. There were some very heavy physical chemistry and quantum chemistry lectures, so it's okay, it's 5 o'clock, you may be tired, so I'll give you a recap at the end. A little parenthesis, I'm so glad to be at KCD. It's my third KCD Munich, because there's only been 3 so far. Who knows who this person was, because unfortunately he passed away. So this is Dan Koh, the late president, director of CNCF, and this was the first ever KCD organized in the world by us in Amsterdam in 2019, just before COVID, right? So, and then lots of people, also Max, reached out because they wanted to do, a lot of cities around the world wanted to organize KCD. Unfortunately, it wasn't possible. Also for us, we had to wait 3 years before doing the second edition of this one. But this was the very first edition of KCD ever happened in the world. So I'm proud of that. At least that's something that I'm proud of. I'm also proud of my scientific achievements, although it's not my career anymore. It's not my professional career. I did want to become a chemistry professor, like many PhDs have this dream shattered. Who is a scientist in the room? Who has background in science, physics, mathematics? It's all the same. It's all different aspects of nature, right? So this is my best article ever written in Angewandte Chemie. It's what I did at the University of Amsterdam. That's the symbol out there. Of course, everybody thinks for sometimes people thought I was Walter White because I was finishing the PhD when the TV series came out. So I had to explain a lot that I was not making drugs for anybody. Being in Amsterdam, though, also didn't help. But no, I never synthesized any drug. I did synthesize a bunch of compounds, and I have infinite love for chemistry, right? So it's really my first love, and something that I'm still today proud of. So what is chemistry? Chemistry, it's a very common definition, is a science of change, right? So chemistry deals with everything that changes the state of physical compounds, and chemistry deals with one important force. So there are 4 forces in the world, in the universe: gravity, weak, strong, and electromagnetic. And chemistry is the science of change with everything involving the electromagnetic force. So all the electrons moving around in chemical reaction, they all do that. They all have this behavior because of the electromagnetic force. So I'm always been fascinated because it's like, for me, chemistry is like having a third eye, right? So having a perspective on the physical world, on the natural world, that I didn't get by just like reading books or poetry and art. It was a way to understand the world around me and change it, because that's what chemistry does. It changes things and observe and explain how things change. So chemistry comes from way, way back. That's Democritus, Greek philosopher. So in Greek philosophy, or in the Greek world, there was a very rudimental notion about atoms, right? So there was the atoms comes from the Greek atomos, which means indivisible. So even then, even the Greek philosopher and scientists, they understand that the world is made of these fundamental things that cannot be divided further. Of course, they didn't have any scientific instruments, so they could not go down to the root cause, to the root atomos that is not divisible. So they had to stop at a very superficial level. But even then, they understood that there was something making everything, right? So there was some fundamental particles, things, they call it atomos, but that was making everything around us. And the very idea of atomos, of course, evolved during the centuries and millennia until the current understanding of what the atom is, which also evolved. So at some point, we also thought the atom was pretty much like the solar system, right? There was they could see inside the atom, and so they realized there is a nuclei, right, that contains most of the mass of an atom, surrounded by what they thought it was more like the planetary theory of an atom, with the electron zipping around pretty much in an orbit around the atom. Now, we know this is not true. Of course, this is science, right? So new theories, new explanations replace the old ones. They don't supplant completely, as in you can explain most of the things you observe in chemistry with the planetary or very simplified representation of an atom. But we know that's not true. It's not what really goes on. And we know now that, yes, there is a central nuclei of an atom, but the electrons are more spread over a quantum cloud of probability. So you can only describe the probability to find an electron as a specific point around the nuclei, but you cannot measure both the speed and the position of this electron. But it's for us, for explaining the periodic table, the idea of a central atom, central nuclei surrounded by a number of electrons is sufficient. So this is the periodic table of elements. This is one of the most important scientific achievements of mankind. It's an amazing piece of work. Seems so simple. It hangs in every lab. I have actually one hanging in my living room because I really like it. I like the order and the regularity that is associated with the natural world. Everything around you, literally everything, is made of this. So this represents very accurately the world around us. So all the elements that forms the matter that is around us. And it's made of 108 elements. There are more to be discovered, but we think we'll reach the limit of the periodic table. There is a few missing, really on the left side, on the bottom left side. But the more atomic mass, so these elements, these are all the elements there are, they are ordered by atomic number, which is the number of protons in the nuclei. There only can be, of course, a integer number of protons in nuclei, so it's 1, 2, 3, 4, 5. Although the number of neutrons in nuclei can change, and does change. So a nuclei made of purely positively charged protons, of course, is very unstable, because positive charges tend to repel each other. So nature finds a way to stabilize higher atomic mass number nuclei elements by adding more neutrons to the core, to the nuclei. And so we have a zoo of elements, like a very diverse, very rich properties of elements as we go across the atomic number. So this was done by this amazing person. It's a Russian scientist, Dmitry Mendeleev. Also, very interesting story. He was born in Siberia. He was the youngest of 17 children. He had to fight all his life for studying and for making an academic career. But he had the vision of ordering the known elements at the time, which were not everything. We didn't know all 108 at the time. But by seeing order in the chaos, he could explain the present. He could predict elements that were not even there. They were not even discovered at the time. So he actually predicted things like technetium and tellurium, I think. But he could order these. Of course, this is very rudimentary. It doesn't look like the one that we are used now. But this is the periodic table, the very first one made in 1811. So what gives elements is their character, their properties, is the number of electrons in the outer shell of the atom itself. So because every atom, of course, has to start from a neutral position. So as many protons you have in the nuclei, you have the same number of electrons in the shell. And the shells they get completed. So there's the Pauli exclusion principle that says that only 2 electrons can occupy every single shell. There are different growing shells of electrons. That's why I'm saying that the simple planetary model is enough to explain the properties of atoms. And that's how we identify. So this is the symbol, and this is the mass number, and this is the atomic number, the number of protons. So the mass number is the sum of protons and neutrons, but what really gives the chemical character to an element is the number of electrons in the outer shell. So I hope I'm not boring you, but I'm very excited by this. And
now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable, halogens and alkali react aggressively. Each period will see new outer shells will electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine, film, while krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the...
I'm not going to bother you, but it's on YouTube. It's super funny. So see everything around us, from the toothpaste to this very computer to our body, is made of these elements, no more, no less. There's nothing mysterious about it, right? So even the origin of these elements is not mysterious anymore. Although for a long time, scientists were puzzled because in the core of stars, fusion can only go up to the iron core. So that's why the supernovas are stars that exhaust their nuclear fuel. Everything is made of iron in the core, and then there's a sudden gravitational collapse of the star, and then all the elements up to the iron are spewed into the universe. And then they were puzzled, where does everything else come from? And now we know it's because what is left after a supernova explosion is a neutron star. Astrophysics is also one of my other passions. So the neutron stars is left is made of a core of pure neutron pasta, they call it. And when two neutron stars collide, they start to orbit around each other. And when they collide, they form most likely a black hole. But most of the mass, a lot of the mass is also rearranged from this neutron pasta into every other element that you see in the periodic table. So if you didn't know where everything else comes from, of course, like there's so little of everything else. Most of the universe is made of about 70% of hydrogen and helium and then everything else in much smaller quantities. But they come from mergers of neutron stars. And you can rearrange the elements as you like, because this is just, it's for us, right? So the elements are the elements, it's how we arrange them that matters to us. It's just a way for us to rationalize the world around us. There are some interesting ways to do this, of course. There's a circular one, but they all start from hydrogen, of course, and then they go around and you can be creative with this. But the map is not the territory. It's just a way for us to understand, to make sense of the world through some nice, regular patterns. The brain is trained to find patterns in the world, right? So that's what we do, and that's what makes us human, and that's what helps us survive. And I think it's the second time you see these slides today. So this is why we are here? Why this guy is talking about chemistry? Because for me, I saw parallelism or parallels between what is the periodic table and the CNCF landscape. So it's just a way. I know everybody's scared, and everybody uses the meme to scare off people, or like don't come this way. It's a bad place. Actually, it's a way to rationalize and to help ourselves and others to find our way through a complex landscape like is the chemistry world or the CNCF landscape. So now for the interesting part, I just made a quick and dirty GitHub repo. So if something is wrong, I'm going to show you some ideas, some comparison between chemical element, and it's going to be like a quiz. But if you have more suggestions, because it's by no means exhaustive, please come in. So, of course, this is not on the landscape, but it is most important. So what would you associate Linux with? Which element? No one? Too simple, I mean. So for me, it's oxygen. OK, you can suggest. So oxygen is everywhere. It makes life possible, right? So it's like Linux makes everything possible in my world, right? So oxygen, of course, is the element oxygen. And what we know most, what we identify as oxygen is the molecule of oxygen, O2. Very important for life on Earth. It used to be poison for life, but today we rely on oxygen. And we haven't found yet a single exoplanet with oxygen atmosphere, so we keep looking, of course. So, what is Kubernetes, of course? This is simple. Carbon, who said that? Okay, you win. So, because carbon is also the basis of life on Earth. And why? It's a very unique molecule in the fact that it can make a variety of different combinations with other elements. As in, it can make a single triple bond, it can make a double bond and two single bonds, and it can make this beautiful structure like diamond in a pyramid shape. So for me, Kubernetes is also the basis of everything, right? So it's a platform to build platforms. So Kubernetes is definitely carbon. So it's not K, it's not potassium, because some people will say. What is Prometheus? This one I choose more from the word Prometheus, the Greek god that brought fire to humanity. So phosphorus is one of the most reactive elements in the first row. It's the basis, of course, of the matches. So I thought the symbol of Prometheus is fire. right? So I think it's, we don't think sometimes, but I noticed after, when I was making this, there's actually a fire in the logo, right? So this is, I think is intentional, right? So, so Prometheus for me is phosphorus. I put together all the service meshes, Knative, all the networking stuff. Anyone? You don't win anything. I mean, just, so silicon. Why? Because silicon also makes very interesting chemistry that connects a lot of different, it gives a rich structure to compounds, right? So when you have, of course, like the sand is made of silicon. We love, of course, our beautiful machines. They're all made of silicon. And that, in the corner, is the most round object ever made by humans, is the perfect sphere. I don't know who made it, but I'll look it up. It's a sphere made of silicon. It's so perfect that the imperfections are really, 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 really small. So for me, because service meshes, they connect things, and silicon kind of makes the connective tissue of chemistry. Again, like this totally random, I just choose it out of my, I woke up one day and said, I think KEDA, what is KEDA? Is an autoscaler, yes. So I compare it to cesium. Now, cesium is a very interesting compound. So I choose cesium because cesium is the element in, now obsolete, of course, atomic clocks, or very, very precise clocks. And for me, KEDA, it gives you this control over your infrastructure. And it's probably one of the weakest analogy I ever found, but I have to feel the stuff. So cilium, I compare it to neon. So there is reason why, and I need to read of course, because I never remember the stuff, because it's because provides advanced networking and security, and neon being one of the noble gases, it gives also light it's naturally bright. So as cilium improves visibility in your stack, neon lights will help you also finding your way at night. Argon, again, I fall back to the normal, the name argon. Argon is one of the noble gases, like neon. They have very interesting properties. So for a long time, actually, the noble gases were not in the periodic table because nobody knew about their existence, because they are so noble and unreactive that we didn't find them for a long time. So the whole last column of the periodic table wasn't even there. There are, of course, lasers made of argon. They help you fix your cornea problems. And so I decided to put argo. No crazy stuff here, just argo. Open telemetry, mercury. So because mercury is a very important metal, so it's the only metal that is liquid at room temperature, right? So, and because of that was used in thermometers, which helps you visualize the temperature of the room. So I thought maybe there's a good comparison with open telemetry. But again, if you don't think it's right, and if you have better suggestions, please contact me. So, and this is Mercury, the planet, which is also, because of the color, was talk about this. So at the end of the talk, so I just want to tell you that, first of all, I'm very grateful for you to be here, but also I'm 48, and I still look at the world with the O, the O. That's why we say awesome, right? So because we need to look at the world with fresh eyes all the time. So see the world in a different way, and be always curious and open to see the world in a different way. That's why I wanted to do this talk, because I wanted to give you a different 30 minutes of something else than just just cloud native. So now you can relax. We can all go to chill. So don't take yourself too seriously. This is science, of course. It's very serious, but in the end, we're all here to have a good time. So if you have any question, you can contact me. And this is what I'm building. And if you want to build something around namespace as a service, contact me, and we can build it together, because that's how we do it, right? So in cloud native. Thank you very much. And if you have any question, I got 3 minutes left. Any question? Chemistry questions? Cloud native questions? Yes.
Thank you very much for this end of the first day. And if you take the analogies you build a bit further, what would be the IT or cloud native equivalent to a dark hole?
To what?
A dark hole, a black hole.
Oh, okay, that's interesting. I can add something along the lines. So, black holes, okay. So there are more projects than elements, right? So we can also find, there are 148 projects now, only 108 elements. So we need to find more things to compare to. I have no idea. We'll find it. Okay. Yes. Oh, that's the black hole. Yeah. That's the destroyer of world. And of course, the universe is going towards heat death. No, so in hundreds of billions of years, the universe will just die down into heat death, and that may be open closed source software and proprietary software. Yes. Ticketing system. Yes. But yeah, find me later if you want to talk about science or astrophysics or chemistry or anything you want, or Kubernetes spaces. Right? Thank you.